He's just attending week, no? Okay, screaming no. Go to YouTube, no? This is like, yeah, okay, fine. Yes. So, okay, Shekhar, I send you the link.
Send. Pass.
Shut up, shut up.
Send. Yeah. Stop
Yeah,
sharing.
sure. Stop
And
sharing. Close the background.
shut up, all of you.
He
After
also
you
shut
share
up.
the link, shut up.
Yes. You realize people can see this later. Fine.
Okay, where fast? Okay, fine. I found it. Uh, Announcements. Where is announcement? Okay, Teams link, Slido link, GitHub link, YouTube link. That is all. Yes. Send. Shut up. Good evening, guys. Welcome to session 4. We'll start the meeting in 5 minutes. We'll start exactly at 5.
For those who join early, go ahead and scan the QR code and answer a live question before we start.
Okay, I expected a lot more answers for yes, but kind of sad. Why 73% of the people saying no to watching Mission Impossible? Kind of very ironic. Anyway, we'll start the session in 2 minutes. If you have any of your friends who are yet to join, inform them. Exactly at 3 or so, we'll start.
I hope you guys can see my screen.
Yes, the screen is visible. Jana, we can start.
Thank you. All right, before we get started, how many of you are going to watch Mission Impossible? Come on, guys. I heard the villain is also an AI, so that's interesting. Okay. Thank you all for coming here. Hope all of you had fun with AI in the previous sessions. AI is artificial intelligence and not America and India here. ODG coming. Right. At the end of today's session, you'll have a good idea of what decision trees are. You can sit back, relax, and watch. I'll make it as interesting as possible so that you guys can remember it for quite some time. Forget decision trees for a moment. Let's say I have a problem. I want to go to Bangalore from Chennai and I need to know whether to take a car, a train, or a bus. So a decision tree is going to help me make my decision. This is a predefined decision tree, and I'm going to use that. I first check if it's too much distance. It's around 400 kilometers from Chennai to Bangalore, so I don't want to drive that much. So I'll either take a train or a bus. If we expand the decision tree over here, I said I'll be taking a train or a bus, this is a public transport. If the cost of train or bus is going to be less than 1,500, I'll consider taking that. Or else I feel my vehicle is going to give much more mileage and it's going to cost me less to go by car. Assuming that trains and bus costs are going to be less than 1,500, I'll check if I have heavy luggage or not. Based on that, I'll decide to go by train or a bus. Because if I have heavy luggage, going by a train will be a headache. Now, I know all these decisions are logically sound, but bear with me for a moment. Can't we do all of this with just some if-else statements in Python? Yes, decision trees are actually easy. However, how did I know that heavy luggage is a condition based on which I'll make a decision? That is a question I'm going to answer in my part of the session. Let's look at another example. I generally like to take tea or coffee. Some of you might like milk, boost, Horlicks, etc. But for simplicity, I'm going to assume tea and coffee. Now, let's say for the past 100 days, we have recorded whether we had tea or coffee, and also the time of the day and how much sleep we got that day. As you can see in this tabular column, we have a collection of data, and the idea over here is to find patterns. I have also plotted about 100 to 150 points over here. I'll let you guys take a look at it. Right. Observe that at 16 or 4 p.m., after that, I usually take tea. So we can separate these two parts of the data and let's split both of these. The second thing you can observe is that I'll either get more than 6 hours of sleep if I have tea, or I'll get less than 6 hours of sleep if I have coffee. So we have classified these three into these three data parts. Let's think about what we just did. We had data about when we took tea, how much sleep we got that day. It makes sense that if you have more caffeine in your blood, you'll get less sleep. So less than 6 hours makes sense. And we have classified them into three parts over here. What's our takeaway from this? If we follow this pattern in the future, if we take a decision whether to take tea or coffee, if it's after 4 p.m., you'll definitely have tea. If it's before 4 p.m., if you want to sleep more, you'll still have tea. If you don't want to sleep that much, you'll have coffee. This Now, how do computers do all of this? Computers like numbers. Now, we need to feed in something to a computer that it can understand and use it to compare and see whether 4 p.m. is a good split or 5 p.m. is a good split. So we need to quantify this. Some terminologies before we go further. The top part of a decision tree is called a root node, and the nodes following that are called decision nodes. And the final part where you make a final decision is called a leaf node. And parts of the tree are called branches. Now, what are features? Features are something that's used to classify things. For example, a phase can be used to classify ice or water, solid or liquid, hours of sleep and time of the day for tea and coffee, in the example I just gave. ECG pulse, MRI scan, CT scan for heart conditions. And decision trees are used in classification problems and regression problems. But majorly, it's used in classification problems. In the following presentation, we'll mostly be looking into classification problems because decision tree is not really great for regression problems. Consider we have data for 100 days, whether I had tea or coffee, and I want to see which feature will split better. We can directly see that 6 hours here is a better split as it classifies 60 days as tea. Let's quantify this. How do we decide whether to use hours of sleep or time of the day we drank tea or coffee to split? We'll answer this question using two methods. One is called Gini impurity. Another one is called entropy and information. I know it sounds fancy. It'll get better, I promise. Right. A node is called pure if it has one class of objects. As you can notice over here, only T is present in this node, whereas it's an impure node will have both tea and coffee. And this node has maximum impurity because it has an equal distribution of both classes, that is tea and coffee. Now, what is Gini impurity? It tells us how impure a node is. Let's see how it is calculated. Now, we calculate Gini impurity for two things. One is for a node, which you can see over here. There are three nodes. We'll calculate Gini impurity for all the three nodes. Second, we calculate for a split for a decision that we make. Here, the question is it before 4 p.m.? We'll calculate Gini impurity for that too. We'll see how. Gini impurity for the parent node given here is 0.331. This is simple math. How did we get this? So Gini impurity's formula says 1 minus probability of t squared minus probability of coffee squared. We'll learn why intuitively this works. Further, let's calculate the Gini impurities of the following nodes. We'll get 0.35 and 0.277. Now, as I said, Gini impurity of a split. A split is a decision that we take. Is it before 4 p.m.? And we say yes or no. That is a split. And that is calculated using the weighted average of the Gini impurities of its sub branch. That is, here you have 70% of the data going, and here you have 30% of the data going. So this Gini impurity will affect the split by 70%. You can think of it like that. Hence, we'll have 0.35 into 70% plus 0.277 into 30%, after which we'll get the Gini impurity. Now, let's calculate the same thing for another feature. What we did before is we calculated the Gini impurity of a split that says, is it before 4 p.m.? Now, we'll look at a different split. What we are trying to do here is to determine which split will categorize the data in a better way. As we said before, this split obviously categorizes data better because it categorizes 60 days as T initially. But we'll see how using Gini impurity. We can calculate Gini impurity for the nodes here. We get 0.331, 0.498. Observe that the Gini impurity is 0 over here. That is because it has only one class, and this is called a pure node. For a pure node, Gini impurity is 0. Gini impurity of the split again is calculated here, and we get 0.199. We know that this split is going to be better, which means the Gini impurity is less, then it indicates that the split is better. Gini impurity is more, it indicates that the split is not as good. So a computer will calculate Gini impurity for two features and say that this feature is better because it has lower Gini impurity, and it will pick that feature to classify data. Go ahead and scan the QR code and lock your answers, please. I'll wait for 1 or 2 minutes. You guys can use a calculator. All right, let's see. Uh, yeah, you guys can go ahead and scan it. I'll show the question. You need to calculate Gini impurity for these two leaves given over here. Okay. All right. I'll proceed further. We'll find out what the Guinea impurities for the leaf nodes are. All right. As you can see, all we have to do is find the probability of tea and probability of coffee for a particular node. So let me explain where the data is going. We have 100 days of data in this node, and as we classify them, 70 days of data goes into the sleep is greater than 6 hours node, and 30 days of data goes into the T node. Further splitting, we'll have 60 days of data and 10 days of data being classified. So for this node, the probability of T is 54 over 60, and the probability of coffee will be 6 over 60, which is given here. And if you calculate the impurity of that node, you'll get 0.18. The second question was to calculate the impurity of this node, coffee over here. We have 10 days where we had coffee and 0 days where we had tea. What Guinea impurity says here is that it should be zero. And why is that? We have only one class here. It's a pure node, which is exactly what we are trying to find out in a decision tree. The whole idea of decision tree is that it wants to classify things. It it wants to classify when you're going to have tea and when you're going to have coffee in the most best possible manner as possible. Uh, let's look at why this works. If we plot Guinea impurity versus percentage of coffee in a node, let's look at some points in this graph. If the coffee class has zero point 0.5 probability and tea should be zero point 0.5 as well, we can calculate Guinea impurity using the formula before and we'll get Guinea impurity as zero point 0.5. Now, what does this tell us? It says Guinea impurity is maximum when you have equal amount of coffee and equal amount of tea. It means this node which has equal amount of coffee, let's say 10 coffee and 10 tea, has not been classified yet. And this unclassified node is useless to us. We need something that is more classified. And Guinea impurity says this classification is not nice. If we look at a point at zero point 0.7 probability of coffee and zero point 0.3 probability of tea class, we can find out that the Guinea impurity is 0.42 and observe that Guinea impurity reduces as we increase the certainty of coffee class. It becomes 0.5, 0.42, 0.32, 0.18. What can we observe from here? We can observe that when we are more certain about a class in a node, the Guinea impurity of that node will reduce to zero. Guinea impurity varies from 0 to 0.5. And let you guys look at the slide for a moment, digest what's going on here. Before I go any further, if you guys have any doubts, please raise your hands. You can unmute. All right. Before we go further, I want to recap what we saw here. We saw what a decision tree does. A decision tree classifies data. It looks for patterns in data. The tea coffee example that I gave, we classify that after 4 p.m., we generally have tea. And the second part, whenever we need more than 6 hours of sleep, we have tea. In less than 6 hours of sleep, we have coffee. After which we saw how a computer analyzes the data, for which we have defined two things. One is Guinea impurity. The second one we are yet to define. Guinea impurity can help us find out which splitting condition is better. One splitting condition for the example I gave was after 4 p.m. And the second one was more than 6 hours of sleep. Whichever is better will have a lower amount of Guinea impurity for the split. And based on that, we can look at the numbers. We can easily say if one is less than two or greater than two, right? Which is exactly what we need to ask the computer to do, right? So we saw Guinea impurity. Now we'll go into entropy. Entropy refers to some notion of randomness. Entropy does the same job as Guinea impurity in a different way. Now, who came up with this formula? Why is this formula nice? I'll not go into the derivation, but I'll try to say how this formula helps us after solving a problem. All right. So the formula for entropy uh, for a particular node is, let's say you have 10 tea and 20 coffee in a node. So the probability of tea would be 1 over 3 and probability of coffee would be 2 over 3. And you can substitute and find the entropy of a particular node, which I have done here. Just like Guinea impurity, we'll calculate entropy for all the nodes and for a split. The entropies of the nodes are given here. As you can see, 79% of tea and 21% of coffee, it can be substituted and you get 0.741. Similarly, 54%, 16%, and 25% and 5%. We'll get a bunch of numbers. We'll make meaning from these numbers, and that's how we build test increase. Right. So the entropy of the split is again the weighted average of the entropy of the classes. The entropy of this node has a weight of 70%, and the entropy of the right side node has a weight of 30%. So 0.775 is into 70% plus 0.438 into 30%. We'll get 0.673. Now, the 0.673 is going to be useful. Let's calculate the entropy for a second split. Now, what we are doing here is the first split and the second split, we want to calculate the entropies of both of them. We'll find out which is more, which is less, and I'll tell you if how to compare the entropy and say which split is better. And looking at this, we can say that this split is obviously better because it classifies T properly. But we'll ask entropy to do that for us. Entropy of the left node is 0. Entropy of the right node can be calculated. And observe that entropy ranges from 0 to 1. 1 means the node has equal distribution of all the classes. That is, 20 tea and 20 coffee in a node means it has equal contribution. And when entropy is 0, the node is pure. That is given over here. Now, since we get 0.998 over here, we can observe that the tea and coffee amounts are very close to each other. We can calculate the entropy of the split for the above split, and we'll get 0.399. Again, entropy is the weighted average of the entropies of the node. The previous entropy that we got from what we did before for the previous split is 0.673. Now, observe that the entropy for this split is less, which would basically mean that if entropy is less, you'll have a better split. Now, how can we think of entropy in a different way? Think of how much bits of information you have to pass through. Let's say you have a class which has only one, let's say you have a node which has only one class, that is 60 tea and 0 coffee. And in order to pass this information, all you need is one bit to say it's full of tea, right? But if you have a node which has 19 tea and 21 coffee, you need more number of bits to pass through this information. And the entropy is higher over there. Entropy is lower when you need less number of bits to pass through this information. This is one way to think about entropy. All right. Information gain is entropy of a node that we calculated minus the entropy of the split for that node. You can see over here, we can calculate how much information gain that we get. It quantifies how much we have learned in a split. If we split for more than before 4 p.m. or after 4 p.m., we need to gain some information. How do we quantify that information? It's the difference between entropies. Now, something about decision trees that's interesting. Decision trees are greedy because at each step, we want to take the best partition possible. Now, once a model grows to its full depth, that is, it classifies each and every uh, possible feat. It classifies each and every possible class, that is tea and coffee, in my example. The tree branches can be removed, or it can we can look at a bigger picture over here. Let's say a split gives us a negative 10 information gain and a subsequent split gives us a positive 20 information gain. The entire branch over there will be giving us a positive 10 information gain, which is good for us. So we'll not be removing that. The second way of optimizing decision trees is called pre-pruning. It's where you set a maximum depth to a tree, after which it will not grow. Now, why do we do this? We don't want decision trees to overfit. Now, till now, I have not told you if decision trees are good or not. Decision trees by itself is not really good. It tends to overfit to data, and you do not want that to happen. You do not want 100% accuracy on your model. You want something close to 90, 95, something like that. All right. Before I proceed further, if anyone has doubts, you guys can unmute and ask. After this, I'll be implementing decision trees in Colab, and I'll still be using the same tea and coffee example. Yeah, Ratna Kumar, you have raised your hand, and Rajalakshmi. All right, cool, guys. Okay, I have custom created a dataset for tea and coffee, which I showed you before. I'll be using the same. I'll be importing NumPy and Pandas library for storing the data. Let's run and see what how the data looks like. We have three columns here. The first two columns are called features, and in the third column is the class that we want to classify. We'll have either tea or coffee. Now, before I go further into the code, I'll explain what the code is about. You have lots of nodes in a decision tree, and you don't know how many nodes a fully grown decision tree is going to have. So, when you're going to be using a function or when you're going to be using something multiple times, it's better to create a class for it, which is an object. And that's what I've done here, a class for a node. And as you know, every class has a constructor method. I have defined several attributes. These are the attributes for a decision node, and these are the attributes for a leaf node. Recapping, a decision node is going to be in the middle of a decision tree, whereas a leaf node is going to be in the bottom. And a leaf node will have a certain class which it has classified. All right. So feature index and threshold of a decision tree. So if you guys remember, I took the example of before than 4 p.m. or after 4 p.m. Right? So using time of the day is a feature, and the threshold will be 4 p.m. Now the threshold can change to 3 p.m. or 2 p.m. So that's how the threshold is going to change. Now what the decision tree is going to do here is it's going to first take time of the day, and it's going to run through possible some of the possible time, that is either 1 p.m., 1:30, 1:15, 2 p.m., something like that, and it's going to find out which part, which at which point of time it can classify it such that as lesser entropy, and that is why we need information gain here. The left part will be the left side of the branch, and right part will be right side of the branch. For a leaf node has a value. Let's say a leaf node has 20 days of tea and 5 days of coffee. It will be taken as tea, a majority. And all right, I hope no one has any doubts about node here. Okay, I think Kavita Pami has a doubt. No? Okay, good. All right. So what the density classifier is going to do is it's going to implement the algorithm for a decision tree. So as we know, we have to initialize the constructor. We'll have a root. It will basically contain the train decision tree at the end. We'll have stopping conditions. I mentioned pruning. We'll set a maximum depth for it. We don't want a tree to grow really big. So, which is why we have set maximum depth. And the self.min samples, what it's going to do is it's going to look at a node. If it has, let's say, 30 samples or 20 samples or less than that, it is not going to split. So, suppose I set this to 20. If a node has 20 samples, I'll make sure that that node is not going to be split. Now, let's go into information gain. Information gain is exactly what I told you before. It's going to calculate the difference in entropy. Over here, there is one small change. You can calculate information gain for a difference in Guinea impurity also. It's just the difference in Guinea impurity and difference in entropy. And you guys can check the formula and the working over here later on. Similarly, entropy and Guinea next will be doing the similar to the formula that I discussed before. All right. So one of the most important parts of the program over here is going to be build tree. What is build tree going to do? It's going to build a tree, and it's a recursive function. I'll try my best to explain it. Okay. So X and Y, we are just separating the features and the targets. X will be the features, that is time of the day and how many hours of sleep you get. Y will be the class. It's either coffee or tea. And number of samples we can get using this function, np.shape. So we'll be checking for the stopping condition that we defined before. That is where how big you want the E to be, the max depth, or the number of samples that you want a node to have. So we'll check number of samples in a node that's going to be passed into this method is greater than what you're gonna specify. And we'll also check the depth. If both of these conditions satisfy, we'll go inside and we'll find the best split. Now, best split is also a function, get best split. I'll explain this in a moment. What the get best split does is it will give you the best split. It'll either say 4 p.m. is better, 3 p.m. is better, or 6 hours is better, 7 hours is better. It's going to compare all of that, tell you whichever is better for this node. After you get that, you can look at the information gain also. Now, the best split may not have an information gain that is greater than zero. So you'll still check that, and you will build the left subtree and right subtree over here. This is the recursive statement. We are calling build tree function inside build tree. Now, when you do that, what happens is you will go in and out inside build tree function, and it will stop when you have number of samples number of samples less than uh, the minimum number of samples, or when the depth goes on until, let's say, 10, and 10 is your maximum depth that you can have. So that's what is going to happen here. And we'll return the node. The node function that we defined before, we need to input a bunch of stuff inside the node function. I'm sorry, node class. Let's go look at that. So we need to give feature index, threshold, the left part of the tree, the right part of the tree, information gain, and value. Value is going to be only for a leaf node. So we'll give that at the end of build tree method. All right. So we are returning the node, and we have given best split as a threshold part, the feature index part, and the information part. Now, can someone guess what type is best split? Yes, it is a dictionary. That's why I've used key here. And for computing the leaf value, which is basically if you have a leaf node and it has 30 copy and 5 T, it will classify that leaf node as copy, and you'll return the value of the leaf node into the node. All right. So what we just did here was we found out a way to recursively build a tree, and now we'll find out how we use functions called get best split to find out the best split. Uh, in the slides before that I used, yeah, is someone speaking? Okay, cool. Okay, in the get best split function, what we're going to do is we're going to find the best splitting condition, and the feature index will basically look at all the features that we're going to go into. Uh, we have, let's say, 2 p.m. is a feature, 3 p.m. is a feature, two and a half, 2 p.m. Basically, time is a feature from any point in the day. Now, you guys might wonder, we have infinite number of points in a day, right? You can have seconds, milliseconds, and you can define that. So we'll only be taking the possible values of time that is mentioned in the data set. So if the data set has 7 p.m., 7 p.m. will be taken. The data set has 6 p.m., 6 p.m. will be taken. If it does not have 8 p.m., 8 p.m. will not be taken to check the best split condition. All right. So over here, we'll be calculating the uh, splitting the data set for a particular threshold. There are two for loops over here. The first for loop is for every feature. Second for loop is for every point. Let's say we have two features, and each feature has number of values. And over here, the hours of day you get sleep is a feature, and that feature has 1 hour, 2 hour, 3 hour as time as the features, as the threshold values. So we'll calculate the information gain for all of those possibilities. We'll look at whichever is the maximum, which you can see over here, and we'll return the best split for which we get the maximum information gain. So the idea over here is to maximize information gain, which is exactly what we call greedy. Now, is greedy going to be the best way to classify things. Maybe if you didn't do the best information gain at this point of the node and did it at a further point, we would have gotten a better classification. But that is one drawback of testing two, which will be addressed in the second half of the session. Okay, so split is just used to split the data. Now, why am I defining a separate method for split? It is good practice to create different methods so that it'll be easier to debug in case you have any errors. If you write it as a single set of code which does not have functions in them or methods in them, it'll be really difficult to debug. Calculate leaf value is to find out the maximum value in a leaf. 20t, 10 coffee, you say t is the value of the leaf. And this is a custom function just to look at the tree that will be made. And we are coming to the learning part. Learning is called fit over here. So what are we fitting? We have a bunch of data points. We are going to fit that into the decision tree. Let the decision tree grow. So you can see the build tree function over here, and we are inputting the data set. And this will basically build a tree, and it will give you uh, the tree which is going to be saved in self.root. All right. The next two functions are there for testing how good your decision tree is. So the whole point of making a decision tree is so that you have a model in which you can input some time of the day and number of hours of sleep you want to get, and you'll get whether you will have to drink coffee or tea. So if the time right now is 5:43, so my decision tree should say I should drink tea. So these two functions will basically do that, and and also note that make prediction is a recursive function. Okay, so we'll get the features separately in X and the values of tea and coffee in Y. And I'm going to use a method from scikit-learn to to break the data set into train and test uh, for training and testing. So as you guys would have known in the previous sessions, I hope training and testing is important because you need to know if you have overfitted or underfitted a data set and when you train. Right. So here I have fitted the T and I'll run the code. Right. So what this says here is that 14.75 is the time of the day, which is 2 hours and 45 minutes. Maybe 2:45 p.m. So if it's before 2:45 p.m., you have and you want to sleep for less than 5.75 hours, you have coffee and stuff like that. So this is just a way to picturize the decision tree. A better way to use decision trees in programs is to use inbuilt functions in scikit-learn. Now, what I did here is from scratch implement decision trees. What I'll be doing further over here is to use scikit-learn, which is just a bunch of functions to make a better tree. Let's also find out the accuracy of our tree. It's around 92%, which is okayish. We'll find out how to make it better in the second part of the session. And all right, so this is what scikit-learn can give us. This is the decision tree that it's saying we are going to get. Observe that 6 hours of sleep, just like we said, is coming over here. Second thing you need to observe is this is around 3 p.m., which is close to the 4 p.m. that we initially thought would be. And uh, if we input the time of the day and how many hours of sleep you need to get, this will give you a correct prediction for the particular pattern. Right. That's it from my presentation. After this, you guys will be seeing how to uh, bring a bunch of decision trees together and make it into a better model. This is called ensemble methods, and Prana will be taking over. Pranav's presentation, I'm sure it's going to be really good. He's used Manon. For those of you who know Three Blue, One Brown, all of his videos are made with Manon. And if you guys come on top of polls, I hope Pranav will give you an intro to Manon later on. Anyone have any doubts? Yeah, if you guys raise your hands, I can unmute. I'll help you unmute and you guys can talk. I'll be sharing the attendance QR code in a moment. Yes, Jared. You can unmute and talk. Okay, we'll begin the next presentation in some time.
I hope you guys got enough time to give the attendance. We will show the attendance again two more times. You can scan it in if you missed here. Pranav, you can start. Start with ensemble methods.
Okay. Okay. Hey guys, this is Pranav, and I'm going to be covering ensemble methods for you guys. By the way, thanks for the shout out, Janu. Hope the presentation is what you thought it would be. And if you guys need to ask any questions, you can ask them on the Slido or during the time where I post the attendance link or during the time when the polls are going on. Okay, so let's start. The agenda for today in ensemble methods would be uh, first we'll be covering bagging and its application in random forests, and we'll cover boosting and its application in ADA boost and XGBoost. Okay, so let's start with ensemble methods. So what is the meaning of ensemble? Ensemble might sound like a fancy word, but it's just another word for a group or a collection. And it's usually used for a group of musicians.
1 second. Sorry to
Yeah.
interrupt. Are you sharing a screen?
Yep, I am.
No, I don't think we are able to see your screen.
Okay, just a second. Is the screen visible now?
No, Pranav, unfortunately. No.
Uh, just give me a second. Let me leave the meeting and join again. See what happens.
Sure. Yes, we can see your screen now.
Okay.
Start.
Okay. Yeah. So where was I? So we're doing ensemble methods. What is the meaning of ensemble? The word ensemble. It's a group or a collection, and it's usually used in the context of musicians. So an ensemble of musicians makes an orchestra or a band or something. So we're going to take this idea and apply it to different models of machine learning. Uh, so when we say we have an ensemble of models, we're trying to combine two models to give you a stronger model, and the stronger model will give you stronger predictions. So that's the basic idea behind the word ensemble and ensemble methods. So before covering any ensemble methods, we'll be covering the concepts behind that, which is bagging and boosting, as I said. So let's start with bagging. Bagging has mainly two different ideas. The first idea is bootstrapping. The second idea is aggregation. So these two ideas combine to give you bagging. Let's see what bootstrapping and aggregation is. So if you look at this animation, you can see that the original data is a bunch of colorful dots, right? So let's say these dots are balls in a bag. So what bootstrapping does is it randomly samples balls from the bag and makes a subset of balls, like another bag, a smaller bag. So what the actual definition is randomly uh, subsetting observations from the original data with replacement. So when I say with replacement, what it means is that you can take the same ball out of the bag twice. In the sense, if I have a red, a green, and a yellow ball in the bag, if I take a red ball out, there will still be a red ball inside for me to take out again. So this is what replacement means. And to illustrate this, if you look on the right side, there is a gold ball twice here, but in the original data, it's there only once. So if you think this is orange, this is gold. Okay. So so what I mean by this is there are infinite copies of each ball inside the bag, so that you can randomly sample with replacement. So so that's it for bootstrapping. The next thing is aggregation. So why are we bootstrapping first of all? We want to give it to different models and take its prediction and then combine it to give you a stronger prediction. So we'll cover what the models are later, but bootstrapping is what this is. But now, how do we combine all of the predictions of each of the models? That part is called aggregation. Now, before we cover bootstrapping and aggregation in detail, we should know that the models can be classifiers or regressors. They can be both. So as you can see, the first part over here is bootstrapping. And the second part, the combination of all the predictions, they're aggregation. Okay, so let's go into the details of bootstrapping. Suppose you have a data set here which has the columns gender, age, weight, and height as the features, and you want to predict something. So what happens is bootstrapping randomly samples from this data set. How does it do it? As you can see, it's taking individual rows and making another subset. And you have also seen that the second and the third rows are the same. This is what with replacement means. So this is one of our subset. Let's keep that aside. So this subset is passed to a model and it gives us a prediction, right? Now, before uh, going into the aggregation part, we'll uh, we'll see one part of aggregation first, the classification or the regression. We'll first look at the classification part. So in classification, say we're classifying if a person has diabetes or not. I know it's hard to classify if a person has diabetes or not with gender, age, weight, and height of a person, but bear with me for a while. Okay, so what happens here is the model to which we pass these three rows predicts yes. We don't know how it predicts yes, but we'll go into that in a while. So these three rows combine to give a subset, and that is passed to a model which gives you yes. Now these three rows also combine and are passed into a model and they give you yes. So these three rows are different. So these three rows have also been found from randomly sampling from the original data, which is bootstrapping. In the next three rows, which are also different, they give you no. Now you have these three predictions and you need to aggregate them. In a classification perspective, how we aggregate is we use a concept of max voting. What is max voting? If you think about how we want to aggregate in using common sense, we'd say, oh, let's say majority vote and say the prediction is yes. That is exactly what max voting is. Why does this work? It works because we're randomly sampling data and giving it to equal models. So none of the models are special. So you're getting a prediction which has the equal weightage. So if it has equal weightage, then you have to give equal weightage during aggregation as well, which is maximum voting. So this is for classification, aggregation in classification. Now, when you talk about aggregation in regression, it's also very simple. First, let's say these are the three rows in the first subset, which gives you 2.5, say 2.5 lakhs per annum or like whatever. We're trying to predict income from these four rows: gender, age, weight, and height. So we're trying to predict income, and this first model predicts 2.5. The second model predicts 1, and the third model predicts 3.5. So how can we aggregate all of these values? Somebody might use common sense and say, let's all average them, which is the exact answer. Why? Same reason as before. None of the models are special. You need to look at each of the predictions equally. Now, one might ask, why do you even need to bootstrap? Just pass one model and get its answer. We have few reasons for why bagging and bootstrapping is useful. We'll cover that now. Moving on to bootstrapping advantages. We're going to cover two main advantages of bootstrapping. And to cover that, I'll give you an example. Firstly, it reduces algebraic calculations. How? Let me give you an example. Suppose you have the heights of 1,000 boys in your school, and you need to compute their variance. I know you wouldn't simply go and compute their variance, but let's say you want to, as an example. Here, variance is the same variance that you were taught in 12th, or maybe 10th, I don't know, which is the sum of the difference between that value and the mean whole square divided by the number of entries. So if you have to compute the variance of 1,000 people, you'd have to compute the square function 1,000 times and then a division function once, right? So instead of doing this, why don't we bootstrap? Take 5 samples from the original data, give it to one model. Take 5 samples from the original data, give it to another model, and give it to 5 different models. So why am I taking just 5 samples? It's random. I could take 10, I could take 15. Why am I giving it to 5 models? Yeah, again, it's random. I could give it to 10, I could give it to 15. But for the sake of example, we're taking 5 and 5. So when we compute the variance, we have we have to compute the square function 5 times and divide it only once. And when we do this 5 times, we have 5 into 5, 25 times we have to compute the variance, as opposed to 1,000 times, which was before. So, which is faster and better? This method. Now, let's think about why this works. So, if you think about it, you have a distribution of 1,000 heights of the boys in your school. When you randomly sample 5 heights, there's always a chance that you could sample uh, from a taller subset, right? Or there's a chance that you could sample 5 of the shortest boys, or there's a chance that you could sample 5 normal boys. In either case, you won't get an accurate variance, which is why we're not doing this once. We're doing it many times. So when we do this many times, probability guarantees that uh, you are going to get a very close value to the value that you might have got when you computed 1,000 heights. So we have all of these variances x1, x2, x3, x4, x5, and this is a problem of regression. So we're going to average them all like so. So this is one of the advantage of bootstrapping. Another advantage is to reduce variance. So if you've attended the previous summer school sessions, you might know what variance is, but I'm going to cover it in short right now. So suppose we have a y equals x square curve, which we need to predict with a group of uh, with a subset of data, and the data is plotted on the curve in the form of these pink dots. You know that they all represent the y equals x square curve, but you know that they all will not lie on the line like this pink dot over here, because worldly data always has noise and it's not 100% accurate, which is why we need models to predict and stuff. So uh, we are reducing variance using bootstrapping, which means our models will have high variance, and high variance means overfitting. And what is overfitting? It means our data is our model is such that it passes through each and every point in the data, which means it's giving a preference which is very high to each and every data point. We don't want each and every data point to change our prediction that much. We want it to we want to give it a little bit of preference, but not a lot of preference. So what overfitting does is try to make a curve that passes through each of the points. So what happens is if I make another point, say here, what does the model do? It passes through that point also. When I make another point, say here, what does the model do? It passes through that also. So what we need to do is to ensure that the model stays the same or similar and doesn't fluctuate with each and every observation. So I'm just doing this a couple of times to illustrate how the curve changes with each and every prediction. So this is what overfitting is, and this is what high variance is. Now, if you think about it, if you take some random data and some random data which sits on the y equals x square curve, average out a lot of these spline curves, what do you think we might get? I think we will definitely get the y equals x square curve. That is very much likely. That is the basic idea between bootstrapping. There's a lot of math involved in all of this, but I don't want to bore you with that. That's another curve. And yes, underfitting. What is underfitting? Say you want to fit this y equals x square curve. This time it's not a complicated curve. It's not complicated at all. It's just a straight line. So what this means is it's underfitting. Underfitting means it's not able to learn from the data as much. So say I tell you to predict if a guy is obese or not, and if I only give you his weight, you the model will say, oh yes, the weight is proportional to obesity and make a straight line. But if I give you some other factors like his muscle mass or whatever, a heavier guy might not always be obese, right? So what we're doing here is saying how the model learns from only one or very few factors, like only the weight. So if we give the model all of the features and it learns from only one, it's not useful, right? So what the model does is it possesses a high bias towards one of its features, due to which it's not able to learn properly. We don't want this either. Okay, next up, random forests. And before we go into random forests, let's look at a poll. You guys can scan the QR code and join the quiz. Okay. I think we'll start the quiz when it hits 100 participants. Simple question. Okay, so these are the answers. Yep. And the maximum vote goes to reduces variance, which is right. Reduces bias and variance. Okay, so this got a unusually high response. So bias and variance are on a very on a different scale. If a model has high variance, it has low bias, and if it has low variance, it has high bias. So they're complete opposites. If you understood, the linear model has high bias, low variance. The spline curve has high variance, low bias. Okay, just go back to our presentation. Okay, so let's cover random forest. Random forest may sound fancy, but it's an application of bagging. Let's see how. So random forest is basically bagging applied on a bunch of decision trees. Let's say we have this data, which again has gender, age, weight, and height of 7 people. I've labeled the columns as features because that's what they are. Another feature of random forest is that it includes row as well as feature sampling. So what this means is you are not only sampling the records, like you're not only choosing row 1, row 3, row 5 and giving it to a model. You are choosing row 1, row 3, row 5, and you are also choosing a subset of features like F1, F2, F3 only and not including F1. So what this does, it adds to the effect of bootstrapping and gives you a more generalized model. Basically, the averaging process that we saw in that spline curve is made easier and more effective, which is what we're going to illustrate here. And what random forest does is it works on a bunch of decision trees. As Jana said before, decision trees overfit and bootstrapping lowers variance. So and it minimizes overfitting. So for the sake of uh, an example, so what we're going to do is give uh, column 2, column 3, column 4, row 2, row 4, and row 5 to decision tree 1. These highlighted rows in pink is what we're going to give to decision tree 1. And to decision tree 2, we're going to give feature 1, feature 3, feature 4, row 1, row 3, row 6, and row 7. And to decision 3, number 3, we're going to give column 1, column 2, column 4, row 1, row 4, row 6. And for decision tree number 4, we're going to give columns 1 to 3, row 2, row 5, and row 7. So as you can see here, the number of distinct rows need not be constant. The number of rows must be constant. But the columns that you're sampling, the features, they must be distinct and constant. That's another characteristic of random forests. And as you know, each decision tree will give you a prediction, which may be yes or no. Say we're predicting diabetes again. Say we're not predicting uh, any regression data. We're classifying into a yes or no prediction for diabetes. Decision tree number 1 gives yes, number 2 gives no, number 3 gives no, number 4 gives no. And as we know, max voting, what's our prediction going to be? No. So the person is not diabetic. That's it for random forests. Simple, right? And now we're going to go into boosting. So before we go into boosting, I just want to share the attendance link. I'm going to pause here for a couple of minutes. You can scan this if you've missed it. Okay. So somebody has asked what sampling means. So sampling means, say, suppose I have a bunch of balls in a bag again. I'm taking 3 balls out of that. That means I'm sampling 3 balls out of that. That's what it means. I'm creating subsets from the original data set. That's what sampling means. How do you make videos like this? You need to write a lot of code, know how Manim works. There's a lot of videos and documentation out there for you to learn. So you can do that. You can contact me later if you really want to know how this works. Okay. So that's the attendance. Let's go to the second poll. This is the second of 3 polls. So if you guys haven't scanned the QR code, you can. Just wait for half a minute. Okay. So we have 66 people answered, and everybody has said we perform row and feature sampling. Most of you guys, which is correct. Let's go back to our presentation. The second part, which I will be covering boosting. So boosting uh, might sound fancy, but it's pretty simple. Let's try to understand this with this example. So as you can see, there's a circle and a hexagon. So what we're trying to do is convert this hexagon to the circle. Say our circle is the prediction that we want, and the hexagon is our wild guess. And we're trying to make this guess better step by step. So what do? We give it to our first model. And what does it do? It transforms the top part to the circle. So you're like, okay, now let's give it to the second model. But what does the second model do? It learns from the mistakes of the first model, which means it looks at most of the errors only of the first model. And it does what it can. Next, we give it to the second model, which looks at the errors of the previous one. And it transforms another line to an arc. And you give it to the next model, which looks at the errors of the previous one, and it makes another arc. So as you can see, the circle is not complete, which is what the case is for most of our predictions. Accuracy is mostly never 100%. And this is basically what boosting does. We train models sequentially to give you a better result from a wild guess. So let's cover the first boosting algorithm, AdaBoost. AdaBoost stands for adaptive boosting. Why? It's because of the same reason that I said before. It looks at the errors of the previous model and adapts itself. So as you can see, this picture is very clearly explaining what adaptive boosting is. You have one model, the errors are given to the next model, and the errors of that model are given to the next model, and so on. You should note here that this is not completely correct. Not only the errors are given, the correct predictions are also given, but they're given lesser weightage. We'll see that in adaptive boosting. So what adaptive boosting does is combines weak learners of low variance to produce a strong learner of high variance. So last time what we did, we combined many weak learners of high variance. We made the spline curve to a y equals x square curve. But here, what we'll try to do is we'll try to transform that one straight line and add many other straight lines to make it our y equals x square curve. If you get what I mean. That's what it means when I say combines weak learners of low variance to produce a strong learner of higher variance. Not exactly high. High is not what we want. It would overfit, right? So when I say weak learners, they're basically models which have poor accuracy due to underfitting or overfitting. If you look at this on the left, it's labeled as stumps, but that's actually a decision tree if you follow the previous session. But this is not actually a decision tree. It's a decision tree which has only one split, only one depth. So such a decision tree is called a stump. It's like if I cut off the tree, you'll have only the stump, right? That's something like that. So linear models are also weak learners, which have underfitting, as I explained before. KNNs, if you follow the previous session, are also weak learners. They can underfit or overfit based on the radius of the KNN, the value of K basically, which I won't be going into in detail because it's out of the syllabus or whatever. So what we'll be using as a weak learner for AdaBoost are stumps. Let's understand this as an example. Suppose we have again gender, age, weight, and height, and we're trying to predict diabetes. So when we're trying to predict diabetes, it's a classification model, right? And what this diabetes column has is the true predictions, so that we can learn from these two predictions to make stumps. So what Adaboost does is it makes stumps, it makes weak learners, so that when a new entry comes, it can be passed through these weak learners to give you a good prediction. So now we need to make a stump first, right? How do we do that? We don't know what feature to split with first. Do we split with gender, age, weight, or height. If you follow the previous session, what we're going to use is Gini impurity, right? So we'll do that. And I haven't calculated the Gini impurity for gender, age, weight, or height. And I'm just assuming that the impurity, the least impurity is the column weight. And so let's split the data with weight greater than 69. This is a regression model. So you have to choose 69 again based on your lowest Gini impurity, which I won't be going into here because we need to learn what AdaBoost is and not Gini impurity. So, let's understand how these numbers came first. So what we understand here is this model classifies anybody weighing greater than 69 as diabetic and less than 69 as no diabetes, which is a very bad model. But this is how we build our model. So as you can see, the first model, the first row is passed into a stump and the weight is greater than 69. And it goes into the diabetes prediction. Fortunately, he is diabetic. But the second row, if you say the weight is greater than 69, it's no. So the person should not be diabetic. But she is actually diabetic. So that is classified as a red number here. So like that, if you add all these numbers, this is what you will get. You can try that. But now we need to go to the next stump. And how do we do that? We need to combine different stumps predictions to give you a better prediction, right? And the next stump should learn from the errors of the previous stump. So what we're going to do is compute that error. Now, I haven't gone into what sample weights is yet. Sample weights is basically telling you how important a row is. So an easy number to say how important a row is to just divide 1 by the number of rows is going to give you a number between 0 and 1, which computers like a lot when they try to process. It's also easy to control because it's not overshooting to infinity or coming down to 0. So 1 by 7 is our initial bad prediction, which we're saying that is the weight that we give to each of the rows is 1 by 7. So now we need to calculate the total error. And how do we do that? We just add the sample weights of the wrongly classified rows. So when we do that, we get 1 by 7 of the second row and 1 by 7 of the sixth row, 1 by 7 of the sixth row. So we get total error as 0.286. Now, what do we do with this? We need to do two things. First, we need to calculate the amount of say. Now, what this amount of say does is it's helpful in two ways. One way is it calculates the amount of importance it should give to the stump when it's aggregating the data at the end. So that amount of say does. And another function of amount of say is it tells you how bad each of the prediction that was made in this stump was, so that it can pass it on to the next stump, and the next stump can learn accordingly. So how did this formula half log to 1 minus t by t come? That has a lot of math to it, which I will not cover. But you can understand that the amount of say should be inversely proportional to the total error. And it is that's what's happening here if you look at the formula. Because you should give lesser importance to a stump has a lot of error and more importance to a stump which has lesser error, right? So when you do that, plug in 0.286, you get 0.92. Now, let's look at our first function of amount of say, which is to correctly predict, to update the weights. So to update the weights, what you do is this: old sample weight into e power minus amount of say or plus amount of say. So you can wonder why we're taking e power something, because what happens is this is a very easy way to quantify a number. If it's negative, it will still stay positive because you're doing e power, and it also stays within our limits, because if you say e power minus, it's going to stay between 0 and 1, and e power amount of say is also not going to be too big because our sample weights and amount of say will also be somewhere between 0 to 1. So this is a pretty nice way to to compute new sample weights. Where this has come from is basically from the definition of error boost. So why does correctly predicted have minus amount of say? And why does incorrectly predicted has plus an amount of say? What you want to do is to give lesser weightage to the models, to the rows which have been classified correctly, so that the next stump will classify it better. So that the next stump won't give it much importance, and it will give more importance to the incorrectly predicted data. In this way, it will classify it better. So that's the reason. And when we plug in the data, just to show you examples, you get new sample weight as 0.14 for correctly predicted and incorrectly predicted 0.72. So 0.14 is a lot less than 0.72, which means our next stump is going to learn a lot from our incorrectly predicted samples. It's going to try to correct it. So our sample weights have been updated. Now, if you look at the table on the left, it's the exact same as what we saw before when we tried to compute the first stump, except the sample weights have differed. So what we're going to do is we're going to compute further stumps in the same manner as I've showed here. And you're going to aggregate all of them. The aggregation part will come to later, but these steps are what we need to repeat. We need to create more stumps, and we need to update the sample weights and calculate the amount of say for each stump. And yeah, this is not the final sample weights. We need to normalize them also. Why? Because see, if you sum all the sample weights in the previous one, which is 1/7 plus 1/7 plus 1/7 7 times, you get 1, which is a good number. But here, if you sum all the weights, you get something greater than 1. And this is actually a sign of the weights going to infinity when you use like around 60 stumps. It might blow up. So you don't want that to happen. So if the sum was less than 1, then it might go to 0, which you also not want to happen. So what you'll do is normalize all the weights by dividing it by the total weight. So that the sum stays 1. So this is our actual new sample weight for corrected prediction and incorrectly predicted rows. 0.075 and 0.387. Let's update that. And now we need to just compute further stumps. But now when you're computing further stumps, you need to use weighted Gini impurity. You can't just use normal Gini impurity. Previous one you could have used because the sample weights were the same for each record. And so each record is equal. But now the sample weights are not the same for each record, which means you need to scale each of the Gini impurity of each record that you're using by the sample weight. So I won't be going into the detail of this, but yeah, this is what you need to do. So that's it for how we train a model to make stumps on AdaBoost. Now, if you have a different test data and you need to predict from this model, what will you do? You'll take all those stumps, S1, say we're making 4 stumps in this case, S1, S2, S3, and S4. So we need to pass this record into all of these stumps and get an answer. So when you pass the record to the first stump, it gives you minus 0.98. Now, why is it negative? It's supposed to be positive. All of these numbers are basically the amount of say of each stump. And when I say minus that number, it means that stump is predicting it as no, as it's wrong, as it's not diabetic. Like the person is not diabetic. And 0.75 as in the person is diabetic. Something like that. So then the sign of the number signifies if the prediction is yes or a no. And now, as we've talked about uh, bagging and bootstrapping, we've also talked about aggregation. And we also know that we need to combine all the predictions of these stumps. So how do we do that? We're going to add them up because each of the stumps are not special. And the specialty of each of the stumps comes from the amount of say, which is already over here by the values. So stump number 3 has less say than stump number 2 because 0.16 is less than 0.75. But because they both are positive, they're saying the same thing, which is fine. But if you look at stump 1, it's minus 0.98, which means it's a very good class. It's a stump which has very low error and it says no. But at the end of the day, we need to aggregate all of the stump's answers. And when we do that, we get 0.06, a positive 0.06, which means we classify the person as diabetic. So this is how Ada Boost works. Okay. So before we go into XGBoost, we have a tiny poll again. Uh, for those of you who haven't scanned your QR code, can do that right now. All right. So let's show you the question. Okay. So most of you have said stumps, which is correct. So fully grown decision trees are the decision trees that Janav showed, which we usually never use. Limited depth decision trees are the ones which we'll use in gradient boosting right now. So stay tuned for that. Let's look at the reader board. So this was the end of all the polls. Let's start with XGBoost. So if we go to XGBoost means extreme gradient boosting. For knowing what extreme gradient boosting is, we need to first know what gradient boosting is, right? So let's learn about that first. So gradient boosting has the word gradient in it. And where have you heard this before? You heard this in gradient descent. And gradient boosting is very similar to gradient descent. It's just that we use different models for decreasing the losses of our predictions. So what happens is each of these lines, each of these decrease in losses is made possible by a limited depth decision tree. And that is basically the crux of gradient boosting. But we'll go into what gradient boosting is in depth with a simple example. So suppose we have gender, age, and house size, and we're going to predict the income of a person. This seems like a better sample of features to predict the income of a person. So that's nice. First, we need to take a random guess, right? So it's clinically proven that the random guess is best when it's the average of all the actual incomes. So these are the training data that we have, and the actual income is 4, 3, 1.5, 3.5, and so on. So it's said that the average is the best one to start the prediction from. There is a simple math behind this, but you can understand that the best way to start our prediction would be from a point which is equidistant from each and every record, right? You don't want the point to start from a record which is you don't want the point to start from close to one record and farther to another record. So you want to start it from a point which is equal, so that you can make equally weighted decision trees. So if you think of that, our first wild guess, our first initial prediction would be 3. Let's keep that in mind. Next, we need to calculate residuals. Residuals, fancy word, but what it means, actual income minus prediction. Very simple. So let's go ahead and input that in our table. So why did we calculate prediction and residuals? Because gradient boosting works in this way. What you do is you fit a decision tree, a limited depth decision tree, to residuals by using gender, age, and house size, or whatever the features that are given as your features, training data. So you're going to predict residuals. So if you think about it, say you predict for row one, say you predict 1 as the residual. What will happen? If you add the prediction to 1, you will get your income. Right. So this is what we're going to do. We're going to predict the residual, add it to our prediction, and try to get income from there. And each time we add the residual to our old prediction, it gets a little closer to our actual income. How does that happen? We use a learning rate, which we'll come to now. So this concept is very similar to gradient boosting if you think about it now. So we need to fit a decision tree to residuals. Let's say this is our limited depth decision tree. As I said before, I haven't calculated Gini impurity and actually made this decision tree after calculation. It's just for the schematic purposes. So what you can see here is each of these rows have been classified into leaf 1, leaf 2, leaf 3, or leaf 4. And at the end of each of the leaves are sometimes multiple residuals. So all of these are residuals. As I said, we're trying to predict residuals. So if the guy has a house size of greater than 2000, and if the guy is no, if the guy has a house size of less than 2000, and if the guy is male, then the residual that we need to add to his initial prediction is minus 2.5. That's what this decision tree basically means. And that's what we've done here. So let's look at the first record. House size greater than 2000, yes. So it goes to the left. Age less than 40, yes. And so it goes to the left. So its residual is added here. But now, say I give you a new record, and that guy also has house size greater than 2000, and that guy also has age less than 40. So what will you say? The prediction is 1 or 0. You don't know. So to solve this problem, usually this problem doesn't arise because in fully grown decision trees, you'll split this node also. This is also becoming a decision node, and you'll get leaves. And there'll be another condition here, and you can classify. But here, what we're going to do is we're going to take the average of each of the residuals in a particular node. That also has some math to it, but we won't go into that in detail for now. Why do we take the average? Because you can think of it as, let's say, uh, the first record has a residual 1 and it's come into this bucket. And the second record has residual 0 and it's also come into the first bucket or the first leaf. You want to classify rows that are similar to 1 or 2, but you don't know whether the classification should be skewed to 1, skewed to 2, or should give equal weightage to both the residuals. As we have a limited number of decision nodes, we can only do justice by averaging or giving equal weightage to both of the rows. And that is basically the idea behind this. But there is some good, nice math behind this where you differentiate equal to 0, maxima, minima, and all that. So if you really want to know about all that, you can contact me. I'll give you good resources. So we average all the residuals. And like I said, we scale we scale the predicted residual by a learning rate, which we're taking as 0.1 here, just for it doesn't have to be 0.1, it could be 0.2, 0.3. It depends on your model and the number of decision trees that you're taking. So so what happens here is you're adding your roll prediction to the scaled value of the predicted residue to give you a new prediction, just like I said before. Now, if this learning rate is 1, then you'll be, say, look at the first row. If learning rate is 1, then you'll be adding 0.5. You'll be adding 0.5 into 1 plus old prediction, which is 3. So you'll be getting your new prediction is 3.5, pretty close to 4. But if your learning rate is zero point 0.1, you'll be scaling that factor down. So let's look at that. So if we take the first row, we need to use the residual of zero point 0.5. And when we try to calculate the new prediction, we get 3.05. And 3.05 is actually good. We've gotten a little closer to the income. But why don't we just make learning rate as 1 and just go to the income directly? That would be overfitting. Why? Because say you have you can imagine that gradient descent curve again, and if you look at the first line and you keep extending it, it goes to a point where you don't find the global minima, right? So what decision trees do, as Jana said before, is they perform a greedy split. They give you the direction, or they give you the prediction which is best at the current point. They give you prediction such that you you can go to the global minima fastest at the current point, but it doesn't actually go to the global minima. It's like taking the good decision for now when you don't know what the best decision is in the long run. So that's what it means. So what you do here is take smaller steps. Taking smaller steps is better than taking bigger steps. That's why learning rate is zero point 0.1. Same thing you can do with the third entry. So you have residual as -2, which stays as -2 because this was the only leaf in this. This was the only entry in this leaf. So when you scale it by uh, your learning rate and add it to 3, you're going to get 2.8, which is again closer to 1 than 3. So we're making progress here. So if we do the same thing for each of the predictions, we're going to get some values. But each of them won't be closer to their predicted value because this is a greedy split and not the best split, right? But in the long run, we will get to the minimum because we're going to use different decision trees, and we're going to correct the errors of this tree. So the first one got a little closer, 3 to 3.5, but the second one got a little farther, 3 to 3.05, which is not closer to 3. So this will be corrected by the further trees. So these steps are what we need to perform in gradient boosting sequentially. So what we do now, we get our uh, we compute our residuals. So we compute our residuals, our new residuals, because we have new predictions. We're going to get new residuals. And now to compute the value of the next decision tree, we need to fit these features to our next residuals. And when we do that, we might get different splits. We might get different decision trees. And we're going to follow the same process for how many ever trees that you choose. Say you choose 4 trees, 5 trees. And you should also note that the trees have a fixed number of leaves. Every single tree has a fixed number of leaves. So this tree has 4. So if you're using 4, every other tree should also have 4. And trees have fixed number of leaves, 8 to 32. This is the industry standard, but we're taking small data set, so we're going to use smaller trees as well. That's basically gradient boosting. Now, how do you predict with gradient boosting? Again, you take a data, you pass it through the decision trees that you've created, just like ADA boost, and those decision trees will give you answers. Now, alpha, you've set before only, it's a hyperparameter. As 0.1, you've set it. And -5 is basically your residual prediction uh, of the first decision tree. So what we're going to do, we're going to scale all of these residual decisions by alpha, and we're going to add it to 3. So when we do this, we get 2.25. Alpha is 0.1, let's say. And 2.25 is pretty close to 2.5 and not exactly 2.5. But yeah, we have a prediction. Now we understood how gradient boosting works. Next up, XGBoost. XGBoost is very, very similar to gradient boosting. In fact, it's just an optimized version of gradient boosting, so it won't take much time in explaining what XGBoost is. So it's an optimized version. It's the industry standard. Basically, mostly people use this model only. It's efficient, fast, and scalable. Scalable to different types of data, different sizes of data, uh, and yeah, basically data from different domains. It's fast because it can leverage parallel computing technologies very well. So XGBoost is a very nice model, but it's basically gradient boosting, but optimized. So why is it optimized? How is it optimized? We will look at two main concepts behind the optimization of XGBoost. One of which is advanced tree pruning and regularization. Parallel processing is one of the features that makes it fast, but it's not something that you need to learn. You know what it is. So let's kind of recap. So we have splits, right? So we do splits on different conditions in different models. For random forests and gradient boosting, we use Gini index, which is basically Gini impurity. For Ada boost, we use weighted Gini index, as I told you before, using the sample weights. And for XG boost, we use a similarity score with regularization. So this is what we need to look at right now. XG boost is different from gradient boosting only in this part. And another small thing which you will look at. So we just need to know what similarity score with regularization is to understand XG boost. So let's go into that. And this is our old tree again. And we're going to try to understand XGBoost from this tree. Firstly, we have similarity score. What is that? It's the square of sum of residuals by number of residuals plus lambda, where lambda is the regularization parameter, which is why it's similarity score with regularization, right? And now you have to note that it's the square of sum and not sum of square. And this will actually play a part when I tell you later. And there's something called information gain, which is the similarity score of the parent minus the similarity score of the right node or the left node, depending on which gain you're talking about. And there's a pruning parameter gamma. So all of this will come into play in additional to the concepts of gradient boost. Let's take this leaf right there, the second leaf, and calculate the similarity score for it. So what happens here is the factors of each of these uh, values cancel out before squaring because we're summing before squaring. So you need to know that. And the denominator is 3 plus 1. 3 is number of residuals. Let's say 1 is the regularization parameter. We get similarity score as 3.38. So we're going to note that. So, so 3.38 is the similarity score for this. And 3.06 will become the similarity score for age less than 40. I'm not showing the calculation for that because I've just showed this and it's very similar. You just need 5 entries as number of residuals and you need to take 1, 0, 0.5, 4.5 and minus 1.5 as the values. So you'll get age less than 40. When you calculate the information gain, you're going to get 0.32, which is basically 3.38 minus 3.06, right? So we're going to keep that also aside. And now we're going to look at pruning parameter. Before going to pruning parameter, we'll look at the regularization parameter and see how it makes gradient boosting better. So what happens is if you use a regularization parameter, your similarity score is going to be smaller than when you use a non when you use a score without a regularization parameter. Because regularization parameters are positive, so it's going to scale down the similarity score. So now when you scale down the similarity score, you have to note that it scales down similarity scores of residuals having nodes having lower number of residuals more and higher number of residuals less. Let's see this with an example. So if number of residuals is 2 and if you calculate the square of sum of residuals, like if you look at leaf 1, you're going to get a value. In contrast to that, if you add 2 and 1, you get 3. So you're going to get a lower value. And if you do the same thing with your leaf number 2, the change of 3 to 4 will result in a lesser decrease in similarity score than the change of 2 to 3. I hope you're with me on this. So what this basically does is regularization. It scales down models which gives more importance to certain rows. So this node here has 2 entries. It should get lesser importance than it's getting if you compare it to the node which has 3 entries. So that's what similarity score is doing. So you can adjust the similarity score to give you a higher or a lower similarity score. But when you use this regularization parameter, it's kind of averaging out the importance given to each of the rows during training. So now the similarity score also has another factor when it comes to pruning. So first, let's look at what pruning is. As Jan said before, we prune a decision node when the gamma, the pruning parameter, is greater than the information gain. Here, the information gain is 0.32. So if we set gamma to 0.3, it won't prune that decision node age less than 40. Otherwise, if you set it to like 0.4, it'll prune the decision node. Now, say you increase your regularization parameter to like 2 or something. What happens? Both your S parent and S right will decrease, correct? Because the regularization parameter is increased. And if both have decreased, then your information gain will also decrease. And if your information gain decreases and your gamma is remaining the same, then what happens is when you increase, when gamma is remaining the same, it will tend to prune decision needs nodes more easily, right? So when the information gains becomes like 0.02 or something, gamma will prune this node. So you have to think about how you set gamma and regularization parameter lambda such that you get a model which can regularize this gradient boosting algorithm by adjusting the importance given to each of these rows so that you get a better model. So this is how XGBoost makes gradient boosting better. Every single one of the other steps that I said in gradient boosting will be followed in XGBoost as well if you talk about regression. So we won't be going into that. And that basically completes our presentation on XGBoost and our uh, summer school session. But before we close, I would like to show you a simple code implementation on this. So I've not implemented all of the classes from scratch. I've just imported the regressors or the classifiers from sklearn, and I've just used them. The first part is about cleaning the data so that we can use them for prediction. So our regression data is a data of Melbourne housing, the housing in Melbourne, and the features that are used for prediction of house price in Melbourne. And a second data, which is classification, is credit score. So what is credit score? It's the
Pranav,
it's the
Pranav,
yeah.
could you zoom in a bit?
Yeah, just a second.
Yeah.
Afraid zooming in. Okay, yeah, it zoomed in finally. Okay. Hmm. So these are the modules that we're using for the import part, and these are the data structures that we're making. Firstly, we're taking the Melbourne housing data, and then we're taking the credit score. Then we're just printing the features so that we kind of understand what the features we are predicting from. So we have suburb, address, rooms, type, price method. Price is what we'll be predicting from all of these: date, distance, postcode. We're going to use all of these features and try to understand how the price is predicted. So we're defining the target column here, and then we're defining the training values, which is the X. You get a Y from the X, and Y is your target column. So another thing is one-hot encoding, where one-hot encoding the data which is not numerical. So for now, for a simple explanation of what one-hot encoding is that it transforms text data to numerical data such that the the computer can understand. So that's what it does at a high level. And we're also new number encoding the credit scores. So if the credit score is low, we're making it 0. If it's average, we're making it 1. If it's high, we're making it 2. So when we do this, it's going to think low is a low value, average is a little higher value, and high is an even higher value. So this is how the computer will understand what to do. And we're also dropping the rows with null values. That's what NaN is. So when we're dropping rows with null values, we make sure that null values don't interfere with our program. So what null values is if you don't have a data, say you have a row with suburb address rooms, but like no type, then we're just dropping that because we don't need it. And we have a lot of other complete rows that we'll use for our prediction. And we're doing the same thing for our target column as well. And we're printing the shape. So if you look at the shape, your regression data has 6,830 rows to predict from and 14,074 features. And our classification has 164, pretty less actually, and 14 features to predict from. And here what we're doing, we're just splitting the data into train and test so that we train from a bunch of data and we'll predict on the test data. The test data is basically the validation data. The val x or val x class, val x reg, val y reg, val y class. Yeah. And so it's very simple when everything is given to you. When all the models are there, you just use it. You fit it. Basically, you predict and you keep this model. Random forest model is a model now which has learned from train x reg and train y reg. Similarly for these models as well. So we're trying to look at a random forest regressor, an ADA boost regressor, a gradient boosting regressor, and an XG boost regressor. So let's look at its accuracies. So when we fit it to our val x reg, which is basically our test data, we're getting an error of this. So the accuracy of a model which uses regression, uh, how you determine it is by looking at the error. So if the error is smaller, it's a better prediction. So if you look at random forest, it gives you this. Then AdaBoost, it gives you a lot more. Which means I told you before that AdaBoost is usually not used for regression. It's only used for classification. So this is that. It has a higher error. Gradient boosting, pretty good. XGBoost, even better. So that's that. And the error metric that we're using to predict this is mean absolute error, which means, say, if you remember the spline curve and the y equals x square curve, the point, if you plot a set of test data points there, then the distance between the actual y equals x square curve and the distance between the spline curve is what our mean absolute error is. We're taking mod of that and we're summing all of that for each of the points. So that's what mean absolute error is. Classification, very similar. We're using random forest classifier, AdaBoost classifier, gradient boost classifier, and XGBoost classifier. We're fitting and we're making the model. And because we had very less data to fit the model on, the runtime was only 1.2 seconds, pretty less. And now when we predict data, we find that random forest is 97.56, pretty good. AdaBoost 100. So usually you don't see numbers like 100, but because our training data was pretty small, it probably learned very well. But yeah, AdaBoost is a very good classifier. Gradient boosting, again 97.56. XGBoost, again 100. So yeah, that's about it for my presentation. Hope you liked it. I'll just display the attendance link one last time for people who missed it. Yep, that should be enough. Okay, let me take a few questions. So a person has asked, you're using a presentation date, how was that made? Yeah, it's not a common presentation software. It's it's Manim, like I said before. There is basically a library in Python called Manim. You download it and you read the documentation, see how it works, and code up each animation on that slide. What are predictions? Okay. Predictions predictions is what we need to do. I mean, AI models are for predictions. You're trying to predict something. Predictions are basically things like predicting the future. It's, how do you say this? Predictions. Google it. Yeah. Bye bye. Hope you liked it. If there are any questions that people need to ask from the meeting, they can. Pawan Raj, do you have any doubts?
Whoever has any doubts, you can stay back in the meet and ask. Otherwise, the session is closed. You can start leaving. We will stay back for another 5 to 10 minutes. If there are any questions, we'll take those doubts and we'll wrap up.
Good evening, sir. I'm Maxine here. Am I audible, sir?
Yes, you're audible. Go ahead.
Yeah, actually, it was a nice presentation. First of all, thank you for this nice presentation. We learned a lot from the decision tree, random forest, everything. Can you please tell me the package used for and this animation, presentation animation? One more time, you can.
Yeah. So it's called Manim, Manim. So you can Google it.
Okay, MANIM. Thank you. Sir, can you please explain about what is inception and exception model?
Inception and exception.
Inception, V3, like that. Oh, it's out of scope. Okay.
No, wait,
It's a
wait.
deep learning model. Okay, sir. Okay, thank you for your presentation. Yeah.
Yeah. Any other questions? Surya Prahash, Pavan Raj, if you have anything to say, now is the time. I guess there are no more questions. So that's about it.
Okay, then we will wrap up the session. I'll end the meeting soon. All the resources are available on GitHub. Uh, Anything and everything. If you have any doubts over there, you can ask on the WhatsApp groups. All the resources you can check on GitHub. That is all. I'll end the meeting now. Thanks a lot, guys, for attending the session.